Then we will move on to a use case, a quantum computer use case from the energy sector. And for this use case, I have the pleasure to introduce two speakers. First is Eva Schramm. She is an innovation professional with experience in technology innovation and ecosystem building. In her role, she leads the technology innovation pillar and open innovation track for peer and cross-industry ecosystems, with a main focus on discovering and establishing emerging technologies such as quantum computing. Give her a round of applause, please. Welcome to the stage, come to the stage. And together with her, there is Dr. Sebastian Senge. He is Accenture's next generation computing lead in the ASG, so the DACH region, and has an extensive background in computer science and is interested in quantum computing, of course, and machine learning. So please come to the stage.
Ist das der?
Das ist der Klicker, genau.
Oh. Good afternoon, everyone. Super nice to be here. I'm Eva Schramm, as already mentioned. I'm working for Elia Group, which is a company in the energy industry. And it's actually quite interesting to talk on a conference about quantum computing, because I can imagine that some people still think this is a field of research that is still far removed from a industry, traditional industry such as the energy industry. But I think it can be a game changer in the future. And that's actually what I would like to also share a little bit with you today, how we think quantum computing can change a really pressing business problem we have. That might also impact you as well as a personal individuum in Germany, for instance, but also how we have applied it. And I'm quite happy that Sebastian is with me today, because we together went through the first proof of concept on quantum computing, and he will demonstrate a little bit or show how we have done this and what the results have been. A few words about Elia Group, because I can imagine not everyone knows. We are a transmission system operator in northeastern Germany as well as in Belgium. And the transmission system operator has three main tasks, I would say, responsibilities. So we are managing the high voltage grid infrastructure, electricity grid, maintaining it and building new infrastructure. We are also, and that's the main part of today as well, operating the system, which means, in very simple words, we keep the lights on. That's our responsibility, that's our mandate. We are a regulated company, and this is a super complex system. There are many, many participants in the system since years, and it's getting much more complex, what we will see as well a bit later. Of course, it's not only a physical system, it's also a market system, so we facilitate the market as well. And I give you one visualization that makes it super simple to explain what a TSO, transmission system operator, is in almost every country. So we are the linchpin between the generation, so the conventional power plants, the wind parks, etc., and between the distribution towards the consumption. So your households or also large industries that need electricity. This is what you can apply basically on every TSO. You might have heard about the energy transition. This is a huge paradigm shift that also impacts us. We are facing this since years already and will be huge in the next years. And this is marked by mainly three major trends. So renewables are replacing the conventional power plants. That also means that they are much more volatile than the conventional power plants before. Secondly, whereas in the past we had still a one-directional value chain for the electricity, so from generation, transported over long distances towards consumption, it will be much more decentralized in the future. That means the generation will come from your rooftops, your solar panels, from your EVs in your garage, from the Porsches we have seen today. So this will be the decentralization. It makes it much more complex than in the past. And last but not least, national borders from countries don't play a role at all. The markets are interconnected on a European level. So we need to deal with these consequences, an exploding number of participants in the system, markets that are much closer to real time, and also, of course, all the requirements, needs that come with this towards us. And how do we navigate through this still uncertain terrain? Not only, but also through technology innovation. And there we are quite strict on how we do this and how we see the benefit of it. We need to be quick in understanding how the technology works. We need to adapt it or reject it immediately if it's not providing any value or the value is not seen for the future. There's a huge pressure on our shoulders, so this is what we have to do. But theory is also not enough. For us, it needs to be hands-on, it needs to be practical, it needs to be linked to a real-world business problem you will see in a minute. And last but not least, if technology disruption occurs in the future, it could hit us very hard. We are already facing problems today, challenges today. What if a technology emerges and we are not prepared? This will be a problem. But let's talk about a real-world problem, as I have promised, in system operation. It's called grid optimization, so an optimal power flow across the system, and more specifically, congestion management. And for the non-energy experts in the room, let me try to explain it in very simple words. We are there to balance the electricity grid. So there is always a balance between generation and consumption. It's a physical phenomenon. If this grid stability is endangered, the transmission system operator takes action. That's our mandate. And these actions can be grid-related or market-related. In very simple words, there's a complex system behind that, but we are either allowed to adjust the generation, the power feed-in, by calling the power plant saying, reduce your generation, it's too much, or we are allowed to redirect the electricity. This is called redispatch, and we will hear it also later. And just to demonstrate the importance of this congestion management problem, optimization problem, I just brought with me some numbers on the cost of congestion management in entire Germany in the last years. And in 2021, you see that there were already 2.3 billion euros congestion management costs in the electricity price. So also in 2022, these figures are not yet published, but we know it's still increasing, although all system operators are already much more efficient than in the years before and are still developing. This is due to the fact that we have much more renewables and we cannot distribute them across the country efficiently. So we need to build lines, we need to transport this. And if you look into the future, on the right side, you see that the expected installed power, renewables, will dramatically increase as well. Obviously, we want to have the energy transition. So that means we not only need to deal with a larger volume of renewables, but also much more volatile power generation. No one can really exactly real-time forecast how solar and wind will act on the system. So that makes it much more complex. These two factors have a huge pressure or increase the pressure on our system, on our optimization. And in simple words, the message is straightforward. A complex system becomes much more complex, more renewables, network expansion, but there are also more different and diverse variables we need to add to our calculation. We need new mechanisms to make greater use of the capacity of the grid. So the objective function for this optimization calculation is much more complex, larger, and also much more diverse, and we need to ensure still the security of supply for this whole society at every second, with increasing also still economic efficiency. Now you could say, where is the problem? Why is this relevant for quantum computing? Just run your calculation a few hours more, then you have time, and you will find the most optimal result for an optimal power flow and optimal congestion management. But time is a luxury we don't have at all. There's in between the ramp-up time of a power plant and the vast effort you have to coordinate all different participants in the system, wind park owners, neighbor countries and their systems, basically everything. There is absolutely no chance for real-time calculation, and therefore no chance to run the calculation as long as you want. So this is a time constraint. There's an interdependency between all these several process steps you have to calculate the congestion management, and also some external factors we cannot foresee, like weather forecasts, etc. So to sum up, I think we can say that the challenge of power grid optimization and congestion management is threefold. It's larger, the size in itself is a challenge. It's much more complex, and we have seen in the future drawing of how this will increase in terms of problem. It will be much more complex, much more volatile. and it has to happen quickly. So for us, this is a strong case actually to think about emerging technologies that can happen quickly. So we are not only testing quantum computing, but for this, we think it can be a game changer in the future, and it will have a large socioeconomic benefit if we can make it happen. That's why we said, okay, it's worth to invest in at least a proof of concept, make it practical, hands-on, and therefore I would like to take the chance to hand over and look a bit how we have done this concretely with Sebastian.
Yeah, thank you very much, Eva, for this great introduction. Which is the green one? Green one? Perfect, right? So, so it works. I mean, the general idea is that exactly what Eva just explained, that for this kind of optimization, some speed up in future might be required, and a potential way in future how this could be done might be quantum computing, right? And to start with, and that is also part of the truth, we definitely need to say that right now there is a lot of hype in the market. We've heard that now a couple of times in the previous session, and indeed that's true. And many quantum journeys start by basically reading statements like this, right? So there will be solutions to intractable systems and disruption everywhere. But what does this actually mean for an organization like Elia, right? And we've all heard narratives like this, that nature is capable of solving intractable or classically intractable systems, and that this could be done in real time and flawlessly and so on and so on. And it's quite natural to ask whether this could be leveraged or not, right? And indeed, there are some good reasons why in future such problems could be benefit from quantum computing. Here is a set of couple of broad use cases that might benefit in future. We've heard already about Hamiltonian evolution, so basically quantum system simulation, optimization, and machine learning. And there is active ongoing research. You've probably heard about this released by IBM a couple of weeks ago. So we are progressing towards quantum utility. Still, there is a lot of debate when the actual advantage will be available. We will see. Of course, I can't foresee that either, as we've heard that already in the previous talks. But why do we believe that there might be some advantage, right? I mean, bear with me, I'm a computer scientist. I like to talk about complexity theory. I do not want to go into all the details here, but at least for exact optimization algorithms and the like, there are quite some good reasons why, at least on paper, algorithms could exist, and partially they were already identified, that could really lead to some big advantages for a couple of use cases. The well-known quadratic speedup of Grover, for example, which probably is not enough for real-world optimization problem, but at least it's something that could be tested, hopefully, in a couple of years. And then, of course, a couple of other exponentially sped-up algorithms, right? But this is not the only piece of the bigger puzzle here, because there are quite a few other factors that are relevant. So, for example, faster gate times, right? And this is difficult to keep track for any kind of organization in the progress in all of these fields. And that leads me to the central idea of my part, that quantum computing today, and most likely in the foreseeable future, is not a simple plug-and-play technology. Instead, companies, especially like Elia, tackle these problems in such a way that they first start with a proof of concept, and then if there's any benefit anticipated, starting an entire dedicated group that looks deeper in such topics. And I'm here today to basically delve into these two topics a little bit deeper. Let's start with the POC. We have seen that already in the introduction by Eva, that this is roughly the setup. So on this part, we see the consumers. In this very simple example, we have a demand of 3,000 megawatt, and as she explained, we need to imbalance in a steady state. Hence, on this side, the producers in total need to produce also 3,000 megawatt. In this simple example, everything is fine, but now let's assume that in a couple of hours in a night situation, the demand drops to 2,000 megawatt. And that actually could mean that in a solution for the producer side, the lower power plant could be switched off, for example, to zero. megawatt, and the other one goes up by 500. So basically you have two changes, and you can do that. Unfortunately, in this simple example, it would lead to a situation where you would have a local overload, a congestion in the power network. And that is, of course, something you wouldn't want to avoid. Roughly something like 1 decade ago, you were able to resolve such a situation manually, and the power plant operators and TSO just called them and aligned on a consensus for the actual power output. Of course, times are changing. We've heard that. We got more and more volatile producers, and especially much more, right? And you can't do that anymore in a local alignment. You need to have an automated way, and that is something that the industry, of course, already implemented in the past years. So on this side, basically, you have the input, basically the demand forecast plus some other information, and on this side you have the output, basically in the example down there, so the optimized power plant schedule that is required to drive the power plants. And in between, the typical tool that has been used in the past years is a centralized optimization. So typically there is some kind of mixed integer linear program that is being used to optimize the overall situation. There are other tools available as well, but this is the standard one, right? And the applications typically being used are state-of-the-art commercial solvers like Gorobi. And since there are quite pretty high costs associated with these number of changes, so the so-called redispatches, Elia, of course, is looking always into ways how this could be improved, right? So the question that Elia basically had, could this problem be formulated as a quantum problem, and could they already benefit from quantum computing today? Well, we implemented this jointly with the stakeholders at Elia Group, and basically we followed the standard process, so starting with a business problem and then gradually turning it into different variants of a mathematical optimization problem, then applying our internal toolkit, which we could use for doing some of the conversions automatically, and then running it on a couple of connected backends. And yeah, here you can see an overview of the typically used algorithms in that area, mostly algorithms that could be applied to analytical formulations of such problems. We also have a very basic implementation of a quantum reinforcement learning where you do not have this type of constraint. But anyway, in this project here, mostly we used these classical optimizers, quantum-inspired, and the standard quantum optimization algorithms to test whether we could get any kind of improvement here. Let's come to the results, and they're typically, at least for real-world problems, they look always typically the same. The problem here is that in real-world problems, you have a large number of constraints, and turning these constraints into penalty parts in the objective typically leads to a situation that, for example, here for quantum-inspired algorithms, you have a accuracy or result quality or solution quality that degrades pretty fast, right? So if you make the system larger and larger and larger, the instance that you use, typically the number of fulfilled constraints degrades rapidly. And we see that for real-world problems, this happens pretty fast, right? I mean, this basically translates to a situation where you just have a couple of time steps and a couple of power plants, and the solution accuracy is already at 0%. And this, of course, could not be used because one of the dramatic effects of that could be that the entire power grid system collapses in Germany, and that's, of course, something we need to avoid, right? So we see that also for other kind of backends and devices. Here, for example, is a result of the D-Wave quantum annealer. The problem here is the same. Basically, the accuracy degrades rapidly, right? So the constraints are basically not fulfilled. In the end, still, it was possible to use a larger number of time steps and power plants here, compared to the classical gate-based algorithms that are typically being investigated. The problem here is, I mean, they lead to correct results. Problem is that the instances are super small, right? I mean, we're talking here in the end about a couple of 1 or 2 power plants and just 3 time steps. You need 1,000 times more of input variables here than could be theoretically calculated right now on the existing systems, right? So now you might say the results are not good. and you're correct. However, from another perspective, and I typically want to say and express that quantum computing is not about quantum computing, and I know this sounds a little bit philosophical, so let's add another word, only, right? And that is the relevant part here. From our perspective, quantum computing is not only about the pure implementation of a problem in a quantum computer, because typically you get the chance, based on all the insights during your project, that you could in the end eventually even improve your classical system. And this also happens here. I do not want to delve into all the details, but the point is we were able to reduce of the classical solution the entire runtime of something like 60 to 70%, right? And this is already some tangible output of such kind of projects. And Elia, of course, wanted now to set up a dedicated team and looking in greater details into such topics of advanced algorithms. And hence we did a second project, and I would quickly like to go through that. It's more or less a strategy project looking into the way how such a dedicated team could be set up. And there are multiple topics we were looking into. Of course, something like objectives and vision and mission. We looked into topics like the actual technologies of next-gen computing which are available today. So for example, neuromorphic computing and some other topics as well. Obviously, we also looked into post-quantum security topics, into operating models, so how really to set up such a team. Then we looked into the topic of ecosystem and partners. We've heard that now multiple times, that connecting with other partners really makes sense in such an R&D topic. And finally, we conducted a use case analysis to plan the next couple of months and years to come to look into different topics that could actually lead to some tangible outcome for Elia Group, right? Yeah, that's it already, what we wanted to share today. In case of any questions to Eva or me, feel free.
Looking at the time, I'm sorry to say that
I'm offline available.
I think both of them will be in the back, and you can ask them the questions directly there. Thank you very much again for giving us these insights.